Hi, you're probably wondering why I'm drinking a smoothie in a video that's supposed to be about math. Well, you're about to find out. My name is Holden, and today I'm going to be showing you how we can use math to turn this into this. Before we get into music, let's talk about heat. Fourier transforms started off as a question about the way heat travels through solid objects. Today, it is the reason we're able to download songs and share pictures using our phones. It's the reason you're able to watch me right now. But before we get into that, we gotta talk smoothies first. But what is a smoothie exactly? Well, it's a smooth drink made up of all types of ingredients, both liquids and solids. Now, if I were at a restaurant and I was having a really good smoothie, and I wanted to know the ingredients that were in it, how can I recreate it at home? Not so easy, right? Well, the Fourier transform does exactly that, only with functions instead of smoothies. While experimenting with the way heat travels through all kinds of solids and metal objects, French mathematician Jean-Baptiste Fourier discovered over 200 years ago that discontinuous functions like temperature distributions could be explained using several continuous functions. An infinite number of sinusoids could be used to express any function, even those with the wildest variations.
This is what a periodic function looks like. It's a periodic function because it has a period that keeps on repeating forever. And now to an example of a non-periodic function. It's not periodic because it does not have a pattern that repeats itself over time. Now don't get me wrong, you can replicate a periodic function, but that's relatively easy because you can create a repeating algorithm. The hard part is when you take an arbitrary function with no general pattern. But Fourier figured out a way to deconstruct non-periodic functions, like those representing a heated metal rod, and express those functions as a collection of sine and cosine waves. Suppose we have a plotted graph of data representing the temperature of a heated metal rod as it changes over time, with x representing the actual metal object and the y representing the temperature in Celsius from least to greatest. Some places are more concentrated or hotter than others, and those places create arbitrary points and an arbitrary curve with no general pattern. So for a metal rod, the ordinate in the graph represents the temperature, and the abscissa represents the boundary points of the piece of metal being used. What Fourier realized is that you could add a third dimension to this graph, and that is the dimension of frequency, or how heated each part of the metal rod becomes in each moment in time. The shape that the summation of the waves make in the new axis is our frequency. In other words, Fourier discovered how to break down any function into sine and cosine functions. Fast forward centuries later, and the Fourier transform is adapted to examine not temperature, but visual images. Take a look at this one.
How did I get it on my phone? And how can I send it to other people overseas? The answer is the Fourier transform,
which deconstructs that image into lots of sine and cosine waves, and the frequencies they make up together. After it's deconstructed, it's sent and then reconstructed on the other side. If we want to start adding cosine and sine waves together, we need a function that creates a summation for every axis we have. In this case, since it's a 2D image, we will use two axes. We need a boundary point because our image ends at some point. We will call them f of kl. Now we need to know where we are adding these sine and cosine waves. We will be doing that in our new axis, frequency, represented as f of ij. This axis determines how dark each pixel should be. The higher the frequency of sine and cosine waves, the darker it is. Now we need to know the resolution of the image, which is represented by n-1. Now we need some kind of pencil so we can actually draw out each sine and cosine wave that makes up our image. We're going to be using Euler's constant in this case. Think of E as our ink to our pen that draws out our function. Now we need the hand to guide the pen to where it goes. We're going to do that by raising e to the negative 2 pi I. The imaginary number is what helps us rotate our pen, because it is a number on the imaginary plane. So it acts as a vector movement, guiding us to where we want to go. Negative 2 pi, which is derived from the equation of a circle, is there to help the vector stay in a rotational matter. Then, we will multiply this exponent by what I call a scaling factor. This is how we determine how much ink we should use, or how dark each pixel should be. Notice how the axis for the frequency domain, known as I and j, which is represented on a different graph, is used in our scaling factor. So is k and l, which is the axis of the actual image we are seeing. This plays a role in letting the function know where the edge of the paper is. The n on the bottom tells us how wide our sine or cosine wave should be stretched in order to fit the image. So that works if we want to store the image as a bunch of sine and cosine waves. Now, what if we were only given sine and cosine waves and the frequency they create? How do we turn all that information back into a picture? Well, that's what this formula is used for. It's the same thing, except the axes are switched, or inverted, hence the name inverse Fourier transform for this algorithm. The n is also inverted, giving us 1 over n squared, squared representing the two-dimensional image. This is just one of the many examples of the ways we can use Fourier transform to analyze any function, ranging from scribbles on a paper to sophisticated portraits. Fourier transform does the same thing with sound. It's the magic behind Spotify. Take a look at this song. Songs can be sent digitally the way they're recorded, but the files are large, since every frequency is preserved in the final track. When songs are broken down from the time domain into the frequency domain, many individual sine waves representing frequency will be revealed. Looking at a Fourier transform of a small piece of a song will show that some frequencies dominate over others, and some are barely noticeable to the ear. Digital sound processing takes those imperceptible frequencies and gets rid of them, along with some on the upper end of our hearing range, that we won't notice if they're gone. What is left behind are only the essential frequencies, or notes, that are necessary for us to enjoy songs. The files are less than a tenth the size of the original recordings, and services like Spotify can share music in neat and practical little files. Converting the problem, or transforming it, makes it easier to understand and easier for engineers to work with. This idea is similar to the idea of using logarithms to make multiplication or division easier.
One possible future use of the Fourier transform might be a device that can detect and deconstruct frequencies of solid objects. That process could help us determine the authenticity of objects that look like they're made of precious metals by comparing the frequencies of the metals in question to the frequencies of, say, real gold, silver, or even platinum. A similar process might be used by geologists looking to identify valuable mineral inside rocks. Being able to separate frequencies into sine and cosine waves for various precious metals could help geologists distinguish rocks that contain valuable minerals from those that don't. The Fourier transform gives us a new perspective on the world we live in, and the mathematical concepts behind it have become fundamental in the digital realm. Fourier's discovery that we could break down periodic functions into a series of sinusoidal functions showed future generations how to manipulate data in all kinds of ways. You could shrink it down, and you could bring it back using reverse engineering of sines and cosines. To this day, Fourier's findings continue to turn chaos into order and have been adapted again and again to promote practical and efficient advancements in countless areas of science, engineering, and technology over the past 2 centuries. As far as what it might teach us over the next 2 and beyond, only time will tell. Thank you for exploring the Fourier transform with me. I hope you enjoyed it as much as I did.